Okay, so in this video I'm going to have a look at deriving the normal distribution probability density function formula. This is it here. We're calling it f of x, which is equal to 1 over sigma times the square root of 2 pi times e to the power minus a half times x minus mu over sigma all squared. Now in this case here we're going to have mu, which is the population mean, and we have sigma here, which is the standard deviation of the population. We can see here as well we've got x minus mu over sigma. That's just a z value, and if we just take a step back first a little bit and have a look at, let's say, our normal distribution of some values that we've taken. Let's take, for example, heights of people. Let's take the mean height as being 170 centimeters, and let's take, so we're going to take our mean here as 170 centimeters, and let's take standard deviation as 10 centimeters just to keep it nice and simple. So we can see our mean here is 170. We can go up here to 180, 190, and out to 200 centimeters, and down here then we would have 160. We just go out a little bit further, 160, 150, and 140 centimeters. So these are the heights of people plotted. We can look at different things on this normal distribution here. For example, if we take someone whose height is let's say 185 centimeters here, what's the probability of picking someone at random? For example, the probability of picking someone at random and that their height is exactly 185 centimeters. Well, we would say that that's really zero, because it's going to be impossible to find someone who has a height of exactly 185 centimeters. You can measure them more and more accurately, and you can find they're going to be slightly off 185 centimeters. So what we can do then is find the probability that someone is, let's say, less than 185 centimeters in height. So by doing that, what we would do is look at the probability of appearing somewhere down here in the graph. And the way we would do that is we would convert that x value to a z value, which is just the x value 185, subtract the mean, which is 170, and divide by sigma, which is 10. And by looking this up in our tables, we would find the probability of appearing in this part of the graph here. Another way of looking at it is if, let's say, we want to find the probability, for example, of someone lying between two heights. So let's say 160, for example, up to 185. So that would be this area here. And up to here. So we'd be looking at the probability of picking someone at random, and their height would be somewhere in that region there. So again, what we could do is just convert these two values to z values again, and look that up in our tables. Now another way of doing that is just to integrate our function. If this was our function f of x here, we could just simply integrate f of x with respect to x somewhere between 160 and 185 centimeters, and that will give us the area underneath this graph between these 2 points here. Okay, so just moving on then to start deriving this formula. The first thing I'm going to do here is just have a look at, let's say, an x and a y axis. So let's draw our y-axis here and our x-axis here. So this is x, this goes on forever in both directions. This is our y-axis here, that goes on forever in both directions. So I'm going to imagine this as a dartboard, and I'm going to throw darts at this, trying to hit the midpoint here. So if I'm trying to hit the midpoint here, some of them will land in around here, others will land maybe not so much out around here, and so on. But the majority of the shots should hit somewhere in the middle here. and they will get less and less dense as we move further out. What we're going to do here is look at the probability of finding a hole or a dart that's hit, let's say here. Actually, I might just do that in a different color, let's say. So we're going to look at the probability of finding a dart that's hit, let's say here. Now what I'm going to do here is just call this particular area here, this is going to be an infinitesimally small area, so we'll call it dA. The distance that this area is going to be from the origin here, let's call it r. What we want to do is find the probability of finding a dart within this area here, this very small area here. What we can do here is look at, as I say, the distance from the origin, which we've called r. We can also look at the x and y coordinates. We can say, well, this is out here x and up along here y, and it has an angle here of theta. Now what I just want to say before we continue is, if we were to take this distance, or let's say out along here, so it's the same distance, or, and we have another area out here, let's call this dA1 for example, and this dA delta A2. The probability of finding a dart in this particular area here is going to be exactly the same as the probability of finding a dart in this area here, so long as r remains the same. The angle isn't going to make any difference. So if we fired enough darts, 1 million, 2 million, 10 million darts, the probability of finding a dart at any particular point here or here is going to be the same. In fact, it's going to be the same all the way around this circle here, so long as r remains the same. It's basically radially symmetrical, if you like. So looking at this particular area here, what I'm going to do is look at the probability density function, which let's say we'll call omega, and that's going to be a function of r times dA. This here is the probability of finding a dart in this particular area here, or this particular area, or symmetrically around the origin, so long as r remains the same. So omega is our probability density function, and what we do is we plug r into that, multiply that by dA, and this gives us the probability of finding a dart in any particular infinitesimally small area, a distance r from the origin. Now another way of looking at this is to look at the x and y coordinates. If we take another probability density function here, let's call it f, what we can do is plug in x and plug in y, multiply them. So the position of the dart in terms of x will have no bearing on the position of the dart in terms of y. So in other words, x and y are independent of each other. We can use the property of independence to write f of x multiplied by f of y, and then we just simply multiply by dA as well. So this will give us the probability of finding a dart in this particular area here, and this will give us the relative probability as well of finding the dart in this particular area here. So what we can do next is just cancel out the dA's. So what we end up with is omega of r is equal to f of x times f of y. Okay, so what we're going to do now is just have a look at this r here. So in other words, this r here. Now r, you can see here, is the distance that the dart is from the origin. So we can rewrite r as the square root of x squared plus y squared. This is a right angle triangle here, so we're just going to use Pythagoras' theorem here. So we got, instead of r, we're going to put in x squared plus y squared square rooted, and over here we still got f of x times f of y. At this stage we've got a lot of variables here. We've got x and y, and we have function omega and the function f here. So what we're going to do now is just try to reduce these down a little bit. The first thing we're going to do here is let y equal to 0. If we let y equal to 0 here, we'll get a constant here. We just plug 0 into f and that'll give us some number, a constant, and also this will be 0 here. So that just means f of y is going to be some constant, and we'll call that constant lambda. So what this formula here becomes then is just omega of x, because y becomes 0, so we just end up with the square root of x squared, so that's just x, and over here we end up with lambda times f of x. So we can see then that if we have omega of the square root of x squared plus y squared, that's just going to be lambda times f of the square root of x squared plus y squared, and we can see from up here that that's just equal to f of x times f of y. What we have here then is f of x times f of y is equal to lambda times f of the square root of x squared plus y squared. So now we are just dealing with f, not f and omega at this stage. Okay, so the next thing I'm going to do then is just divide both sides by lambda squared. So I'm going to take f of x times f of y. I'm going to divide that by lambda squared, and I'm going to divide it in the form lambda times lambda on this side, and on this side lambda times f of the square root of x squared plus y squared. I'm going to divide by lambda squared. So you can see here we've got f of x over lambda times f of y over lambda, and that's just equal to f of the square root of x squared plus y squared all over lambda. This lambda will cancel with one of these lambdas here. Okay, now what I'm going to do now is just introduce another function here, and I'm going to call it g of x. And what I'm going to say is let g of x be f of x over lambda. We don't want another function here, but we will find that it is useful later on. You can see here that g of x is just a scalar multiple of f of x here. In other words, multiply f of x by 1 over lambda here, you'll get g over x. So what we've got here then is g of x times g of y is equal to g of the square root of x squared plus y squared. So in order to solve this, we're going to look at a different kind of function. We need to look at a function that will work here. So a function that will actually work here are exponential functions. In particular, I'm going to look at e to the power of x and e to the power of y, just to show you where that's coming from. If we take, for example, let's say 10 to the power of x, if you multiply that by 10 to the power of y, you'll get 10 to the power of x plus y. Now we have an x in here, a y in here, and we have an x squared plus y squared here. So we're kind of on the right track here. And remember, we're multiplying these two here. So let's look at 10 to the power of x squared times 10 to the power of y squared. That'll give us 10 to the power of x squared plus y squared. So we're a little bit closer now. We have our x squared plus y squared on this side. This will in fact work for any base, of course. If you have, let's say, any base, let's call it b, and we raise that to the power of x squared, multiply that by b to the power of y squared, that'll give us whatever base we use to the power of x squared plus y squared. In this particular case, where I'm using any base here, the b to the power of x squared can also be written as e to the power of k x squared. So we can show how this works by taking the log of either side. So we can take the log, let's use the natural log of b to the power of x squared. Take the natural log of the right hand side and we'll just end up with kx squared. Now we can take this x squared and bring it down here in front of the log. It's one of the laws of logs. So we have log of b here, and on this side we still have kx squared. We can divide both sides by x squared, and that'll finally just give us the log of b is equal to k. So this particular number here, this k here, this constant here, is just simply the natural log of whatever base we decide to use. What I'm going to do here is just test this out. So what we have is g of x times g of y is equal to g of the square root of x squared plus y squared. And what we're saying now is that g of x is just going to be e to the power of kx squared. So let's just substitute that in and see does it work. So we have g of x here, so that's going to be e to the power of kx squared. We have g of y here, so that's going to be times e to the power of ky squared here. And then on the right hand side we've got g of the square root of x squared plus y squared, so that's going to be e to the power of k times the square root of x squared plus y squared all squared. Now let's check to see does this actually work. Would this actually be the case that e to the power of kx squared times e to the power of ky squared is equal to e to the power of k times the square root of x squared plus y squared all squared? Well, we would have here e to the power of kx squared times e to the power of ky squared is equal to e to the power of k times, well, we're just squaring a square root here, so we just end up with a squared plus y squared on this side. That will give us e to the power of kx squared times e to the power of ky squared here. And then on the right hand side, just multiply out the brackets, we end up with kx squared plus ky squared here, and we can see here that we can either split this up or we can just add the indices here. So I'll just add the powers here. It's got e to the power of kx squared plus ky squared is equal to e to the power of kx squared plus ky squared. So it does actually work. If we substitute e to the power of kx squared in for g of x, it does actually work. If we come back up here, we can see that we originally had g of x is equal to f of x divided by lambda. So let's just have a look at that again. So we have g of x is equal to f of x divided by lambda. Now remember, we didn't really want another function here, g of x, so we're going to get away from that now. So we can see here that we would have lambda times g of x is equal to f of x, and we now have a function for g of x, so we can say now that lambda times e to the power of kx squared is equal to f of x. So now we've gotten rid of our g of x and we have this function here now. Okay, so what we have to do now is just ensure that the k here is negative, because if k was positive, that would mean this power here would be positive, which means as x gets bigger and bigger and bigger and goes out into infinity, this number here would just explode. It would just get bigger and bigger. So if k was negative, this would effectively be a fraction, so we would have the denominator getting bigger and bigger and bigger, so the fraction itself would get smaller and smaller and smaller as x increases. So we want k to be negative. We have f of x is equal to lambda times e to the power of k times x squared, and as I say, we need k to be negative, so let's just call k another letter, let's say m. Let's square it to be sure that it's positive, and then put a minus in front of it to ensure that it's negative. So what we have then is f of x is equal to lambda times e to the power of minus m squared times x squared. This particular function here, because it's a probability density function, will have an area underneath the curve of 1. So if we have our function, it will look something like this, and it'll come down here and here, and the area underneath this curve will be 1. So in other words, if we integrate this function here, we should get 1. So if we take, I'm going to take lambda outside the integral. So I'm going to take lambda, which is a constant outside the integral. And then I've got e to the power of minus m squared x squared here with respect to x, and that's going to be equal to 1. So we've got to perform this integration here. So what I'm going to do is integrate by substitution. So I'm going to let u equal to mx. That means du dx is just going to be equal to m, or du is going to be equal to m dx, and also dx is going to be equal to 1 over m du. So let's see what we have then. We have our function here. Let's write it down again. So we've got lambda times the integral of, and remember this is from, I should say, minus infinity to plus infinity, minus infinity to plus infinity here. It's going to be e to the power of, now remember u is mx, we have an mx squared here if you like, and it's negative, so it's going to be to the power of minus u squared here, and then we have dx, and I have a dx here, so that's 1 over m, and then that's, with respect to u, that's going to be equal to 1. Okay, so next step, let's take the 1 over m outside. That's a constant, so I have lambda over m times the integral from minus infinity to plus infinity of e to the power of minus u squared with respect to u, and that's equal to 1. This particular integral here, the integral of e to the power of minus u squared with respect to u, is a famous integral, and I have actually done that integral in a separate video. I think I've called it the Gaussian integral, so you can have a look at that if you like. I'm not going to go through it again here, but it's just going to be equal to the square root of pi. So what we end up with here then is lambda over m. All of this just becomes the square root of pi, so this is just the square root of pi here, and that's equal to 1. So that gives us, if I just mess around with that a little bit, I get lambda times the square root of pi is equal to m, and then just square both sides. I'll end up with pi times lambda squared is equal to m squared. Okay, so what does that give us then? That gives us our function, our final function f of x is equal to lambda times e to the power of minus pi lambda squared x squared. Remember, we had a minus m squared there. So this is our function f of x. Now let's just have a look at this. We're not quite there yet. We still have a bit to do, but we're almost there. If you take our graph of our probability density function, again like this, and if you take lambda being here, so let's take this as being our lambda. So in other words, x is equal to 0 here, so if you put x is equal to 0 here, you'll get e to the power of 0, which is 1, so our y value will just be lambda. So this is our lambda here when x is equal to 0. Now the area underneath this curve is 1, So what we're going to look at now is the spread of the data, or the variance. If we increase lambda, let's say we take a new lambda up here, let's call it lambda 1. In order to maintain the area under the curve, the spread will have to decrease, so it will have to come down maybe something like this. And if we take another lambda, let's say we reduce lambda, let's call it lambda 3, then the spread will have to end up with some kind of a curve like that, with a broader spread, just to maintain the area underneath the curve as being 1. This means that our variance, and indeed our standard deviation, is going to be related to lambda. Now we're going to look at variance, which is sigma squared. So our sigma squared, our variance, is defined as the integral from minus infinity to plus infinity of the difference between the x values and the mean squared times the function itself with respect to x. So in our case, our variance will be the integral from minus infinity to plus infinity of x minus mu squared, and our function is lambda times e to the power of minus pi lambda squared x squared. We want to integrate that with respect to x. This is our sigma squared. So what we're going to do is try and find a relationship between sigma and lambda here, because we want to get rid of this lambda in our final formula. If we have a look at this now, we know that in this case our mean, our mu here, is going to be 0. So we have lambda squared from minus infinity to plus infinity. Here we just end up with a 0 here, so that's just going to be x squared. And then out here we might just take this lambda here and put it outside the integral sign, so I'll put the lambda out here, and we have e to the power of minus pi lambda squared x squared dx. So this is what we've got to integrate. Okay, so we're going to integrate this by parts. We're going to integrate by parts, and remember, to integrate by parts, our formula will be the integral of u dv is equal to uv minus the integral of v du. So this is our formula for integrating by parts. We're going to let u equal to x, and so what we're going to do here is just split this x here up into x times x. So our u will be one of the x's, and then we look at the rest of it as dv. So if u is equal to dx, that means du dx is equal to 1, or just du is equal to dx. On the other side then we have dv is going to be the rest of it, which is our other x, times e to the power of minus pi lambda squared x squared dx. So that's our dv. So we've got to work out what v is then by integration. We've got to basically integrate this side here. So if we integrate the right hand side, what do we get? Well, I'm just going to do it by inspection really. If you have a look at this here, we have an e to the power of something here. So when you integrate e to the power of something, you get e to the power of whatever the something is, and a little bit more as well. We're going to have to do a little bit with it. So let's just guess what it might be first. I'm going to say that it's going to be e to the power of minus pi lambda squared x squared. Now if I say that's what v is, let me just check that by differentiating this here. I'm going to differentiate this and see what I end up with. Well, if I differentiate that, I'll get, just do it over here, I'm going to get e to the power of minus pi lambda squared x squared. Now because it's not e to the power of x, it's e to the power of some function of x, we need to differentiate the power. So if I differentiate the power here, what I end up with is minus 2 pi lambda squared x. I have this part here, but I have an extra bit here. that I don't need. So I'm going to have to get rid of that bit there. So how am I going to get rid of that? Well, I'm going to put in a minus 1 over 2 pi lambda squared here. And now when I differentiate this, I should end up with this here exactly. Okay, so let's do this integration then by parts. Okay, so what I end up with is sigma squared is equal to, lambda is going to be on the outside here, and inside here I got u times v. Well, u is x, and then the v is minus 1 over 2 pi lambda squared. So I'll actually put it all together. I think x over, it's going to be minus 1 over 2 pi lambda squared e to the power of minus pi lambda squared x squared, and then I have minus the integral of v du. So that's going to be minus the integral of minus 1 over 2 pi lambda squared e to the power of minus pi lambda squared x squared dx. And remember, this is all from minus infinity to plus infinity here. Now, if we have a look at this here, we'll find that as x goes to infinity here, this entire thing becomes 0. So this entire thing here becomes 0. So all of this here will just become 0. So really what I've got to do here is just look at sigma squared. It's going to be equal to lambda times the integral from minus infinity to plus infinity. Remember, we have a minus times a minus here, so that's just going to be plus. So we have 1 over 2 pi lambda squared e to the power of minus pi lambda squared x squared dx. So this is the integral that we actually have to do here. Now what I'm going to do here is just swap these two around, because these are both constants, so I'm just going to swap them around. I'm going to end up outside the integral sign here with 1 over 2 pi lambda squared times the integral from minus infinity to plus infinity of lambda times e to the power of minus pi lambda squared x squared dx. And this is our variance still here. If we just have a look at this integral here, this we can find is just our function, and its area is just going to be 1. The area underneath this function here is just 1. This is our function here, and we know that the area underneath the curve here is just going to be 1. So when we integrate this, we should just get 1. So we can replace this here with just 1. So we got sigma squared is equal to 1 over 2 pi lambda squared. Okay, so if we just manipulate this a little bit, we can get lambda squared in terms of sigma. So our lambda squared here is just going to be 1 over 2 pi sigma squared. So we can see here that lambda and sigma are actually inversely proportional. We have our constant here, 1 over 2 pi. So what we worked out was that lambda squared is equal to 1 over 2 pi sigma squared. That just means then that lambda is equal to 1 over sigma times the square root of 2 pi. So let's just substitute these into our formula. So we have f of x is going to be equal to 1 over sigma times the square root of 2 pi e to the power of minus of x squared on the top, and on the bottom here we'll have 2 sigma squared. The pi's will cancel out, so that will give us 1 over sigma times the square root of 2 pi e to the power of, we put the minus half out here, and then here we've got x squared over sigma squared. Now this is our formula for f of x, where the mean is going to be 0 and our standard deviation is going to be sigma. If we were to look at our curve again, we would have, if we were to look at our curve again, we would have a mean here of 0, and our graph would look something like that. Our standard deviation here would be sigma, 2 and 3 out here, 2 sigma, 3 sigma here, minus 2 minus 3 out here. This formula is a probability density function formula when mean is 0 and our standard deviation sigma. But what if our mean is not 0? What if our mean here is, let's say, something else? So let's say it's mu. So here we would have 1 standard deviation above mu, 2 standard deviations, 3 standard deviations above, 1 below, 2 below, 3 below, and so on. But this time our mean is mu. Well, I've done some videos on transformations, functions and transformations. So what we would actually end up with is f of x is equal to 1 over sigma times the square root of 2 pi times e to the power of minus a half, subtract the mean, square it, and you're going to divide by sigma squared here. So this is actually the formula that we set out to derive, and this is where you have a mean of something else other than 0, so a mean of mu, for example, and a standard deviation of sigma. Okay, and that's it for this particular derivation.